Trident. Two missiles launched from a nuclear submarine can hit a target 4,000 miles away with the accuracy of about a football field. That's already absurd. But here's what makes it actually impossible. The submarine that fired it doesn't know exactly where it is. It can't use GPS, saltwater blocks the signal. It can't use radio. It can't use the stars. It's been underwater for 60 days. And yet, somehow, the missile still lands on the target. The way submarines solved this problem in 1960 is one of the most beautiful pieces of engineering ever built. And almost nobody knows it exists. This is how they do it. To really feel why this is so hard, picture yourself in the same situation as a submarine crew. Imagine you're inside a sealed metal tube. No windows, no internet, no phone signal. The only light in the world is whatever you brought with you. And you've been there for 2 months. Now imagine you have to know exactly where you are at all times, within feet, while moving, in a space the size of 2.5 times the surface of every continent on Earth. This is the daily reality for the crew of a nuclear submarine, and the way they actually solve it isn't just clever engineering. It's a 100-year-old idea, a piece of glowing pink helium, and a mathematical trick that punishes the smallest mistake. Let's start with why GPS doesn't work down there. There's a common assumption that satellite signals just have a hard time reaching the bottom of the ocean. The reality is more brutal than that. Saltwater is one of the most aggressive blockers of electromagnetic energy in the natural world. The frequencies GPS uses, around 1.5 gigahertz, get absorbed by seawater within centimeters of the surface. By the time you're at the depth of a periscope, the signal is already dead. By the time you're at operating depth of around 800 to 1,000 feet, it might as well not exist. It's not just GPS. Almost the entire radio spectrum is locked out. Cell signals, Wi-Fi, AM and FM radio. The submarine is blind. There is one narrow exception. Very low-frequency radio waves around 3 to 30 kilohertz can punch through about 10 to 30 meters of seawater, and extremely low-frequency waves in the range of 3 to 300 hertz can reach hundreds of meters down. The United States Navy ran a system called Project ELF for decades, transmitting at 76 hertz from antennas in Wisconsin and Michigan that were several miles long. But here's the catch. These signals are so slow that a single 3-letter message took about 15 minutes to send, useful for telling a submarine to come to periscope depth, useless for navigation, so the submarine has to figure out where it is on its own, with nothing. The foundation of the solution is something sailors have been doing for centuries. It's called dead reckoning, and it's elegantly simple. If you know where you started, and you know exactly which direction you're going, and you know exactly how fast you're going, and you know exactly how much time has passed, then you can calculate where you are. No external reference required. For most of human history, this was done with a compass, a log line thrown overboard to estimate speed, and a stopwatch. It was good enough for Christopher Columbus to find the Caribbean. It is not good enough to launch a nuclear missile at a target halfway around the world. The submarine version of Dead Reckoning needed to be 1,000 times more accurate, and that's where the engineering gets beautiful. The first piece of the puzzle is something called an accelerometer. An accelerometer measures acceleration, any change in motion in any direction. If you have ever felt yourself pressed back into a car seat, as the driver hits the gas, you felt what an accelerometer feels. The submarine has very precise versions of these mounted along 3 perpendicular axes. One for forward and back, one for left and right, one for up and down. Now here is the math trick. Acceleration is the rate at which your speed changes. So if you measure acceleration over time and add it all up, you get speed. That is called integration. Do it once, and you get velocity. Speed isn't enough though. You need position, so you integrate again. Add up all the velocities over time, and you get distance traveled. 2 integrations, and you have turned a measurement of how hard the submarine is being pushed into a measurement of where the submarine is. This sounds straightforward when you say it fast. The reality is that any error in the original acceleration measurement gets amplified twice. A tiny mistake in measuring acceleration becomes a small mistake in velocity, which becomes a much bigger mistake in position. Run that for 60 days, and a microscopic flaw in the accelerometer becomes miles of uncertainty. So accelerometers alone aren't enough. You also need to know exactly which way the submarine is facing. Not approximately. Exactly. Because if you think you're heading north but you're actually heading north by northeast, even a tiny angular error means you're calculating the wrong direction of travel. Multiply that by hours of motion, and you end up in the wrong ocean. This is the gyroscope problem. For most of the 20th century, gyroscopes were mechanical, a heavy spinning wheel mounted on gimbals using the conservation of angular momentum to maintain a fixed orientation in space. They worked, but they had problems. The bearings produced friction, the wheels slowed down, the whole system drifted as parts wore. For a navigation system that needed to be accurate for weeks at a time, mechanical gyros were a constant source of error. What the engineers needed was a gyroscope with no moving parts. Something that could measure rotation using physics so fundamental that it couldn't drift. Something solid state. In 1963, two American physicists named Mossack and Davis demonstrated something that would change everything. The first working ring laser gyroscope. Here's how it works. A ring laser gyroscope is a triangular cavity, often just a few centimeters across, carved into a solid block of special glass that doesn't expand or contract with temperature changes. Inside the cavity is a thin tube filled with a mixture of helium and neon gas. When you run an electrical current through it, the gas glows the distinctive pinkish-orange color of a neon laser. Two laser beams are generated inside this triangular path, traveling in opposite directions. One goes clockwise, the other goes counterclockwise. When the device is sitting still, both beams travel exactly the same distance. They take exactly the same amount of time. They have exactly the same frequency. But the moment the device rotates, something strange happens. The beam traveling in the same direction as the rotation has to travel slightly farther to complete its loop, because the finish line is moving away from it. The beam traveling against the rotation has a slightly shorter path, because the finish line is moving toward it. The two beams, which used to be perfectly synchronized, develop a tiny frequency difference. This is the Sagnac effect, named after the French physicist Georges Sagnac, who first demonstrated it in 1913. The frequency difference between the two beams is directly proportional to how fast the device is rotating. By measuring that frequency shift with extreme precision, the gyroscope can detect rotation rates so subtle they would be impossible to feel. We're talking about angular changes measured in thousandths of a degree per hour. The best modern ring laser gyroscopes have what's called a bias drift of less than 0.001 degrees per hour. That's so precise that if you stood one of these gyroscopes on a perfectly still table, it could detect the rotation of the Earth itself. A submarine has 3 of these mounted at perpendicular angles. One for pitch, the rotation that tilts the bow up and down. One for yaw, the rotation that swings the bow left and right. One for roll, the rotation that tips the submarine onto its side. Together, they can sense any change in orientation, no matter how small, with no moving parts to wear out and no external signal to lose. Combine 3 ring laser gyroscopes with 3 precision accelerometers. Feed all of that data into a computer that runs the math constantly, and you have something extraordinary. You have a system that knows from a known starting point exactly how the submarine has moved through 3-dimensional space. Every shift in heading, every change in speed, every dive and every climb, all recorded, all integrated, all accumulated into a continuously updated position estimate. This is called a strap-down inertial navigation system. On a submarine, it's known as SINS, the ship's inertial navigation system. The first version of SINS was deployed in 1960 on the USS George Washington, the first American nuclear-powered ballistic missile submarine. It was the technology that made the entire Polaris missile program possible. Without it, you couldn't launch a missile from underwater and expect it to hit a target on another continent. The original requirement was for the missile to land within 1 nautical mile of its target. after a flight of more than 1,000 miles. SINs made that possible. Modern Trident submarines carry 3 independent SINs units. 3, because if one fails, the other 2 can be cross-checked against each other. Redundancy is a sacred concept in submarine engineering. There is no roadside assistance at 600 feet under the Atlantic. But here's the thing, nobody mentions about inertial navigation. It still isn't perfect. Every gyroscope, no matter how precise, has some tiny amount of bias drift. Every accelerometer has noise. The math is exact, but the inputs aren't. So errors accumulate slowly, almost imperceptibly, but always. The exact accuracy figures are classified, but the publicly stated drift rate for top-tier ring laser gyroscope inertial navigation systems is around 1 nautical mile per hour of position uncertainty. That sounds tiny, but run it for 3 days of submerged operation, and the submarine could be nearly 70 miles off where the computer thinks it is. That's not unacceptable. So the engineers added another layer. Inside every nuclear submarine is a system called a fathometer. It's an active sonar pointed straight down at the seafloor. It pings a sound pulse, listens for the echo, measures the time delay, and calculates the depth of the water beneath the submarine. Modern submarines use this constantly, painting a picture of the bottom as they pass over it. Now here's the elegant part. The seafloor isn't flat. It has mountains, valleys, ridges, canyons, and abyssal plains. Each region has a unique bathymetric fingerprint, a specific pattern of depths and contours that exists nowhere else on Earth. The submarine carries detailed maps of these patterns in its computer. As it travels, the fathometer compares the depth profile. It's measuring to the patterns in its memory. When it finds a match, it knows exactly where it is. This is called bathymetric navigation, or terrain matching navigation. It's like fingerprinting the ocean floor. The same principle works with the Earth's gravity field. The planet's gravitational pull isn't perfectly uniform. It has subtle variations caused by the distribution of dense rock and water beneath the surface. Submarines can carry gravimeters that detect these variations and compare them to gravity maps. Same idea, different fingerprint. Some Soviet-era and modern Russian submarines also use magnetic anomaly maps. The Earth's magnetic field has its own pattern of dips and ripples, and those patterns can be matched too. So now we have a picture of what's actually inside the navigation rack of a modern nuclear submarine. 3 ring laser gyroscopes, 3 precision accelerometers, a fathometer, sometimes a gravimeter, sometimes a magnetometer, all feeding into a sensor fusion computer that runs a Kalman filter, a piece of mathematics so important that it was used on the Apollo missions to land humans on the moon. The Kalman filter takes all of the noisy, slightly inaccurate inputs from every sensor, weighs them against each other, and produces the single best estimate of where the submarine actually is. And then, every so often, the submarine cheats. When conditions allow, the boat rises to periscope depth. It raises a small mast above the surface for as little as a few seconds. On that mast is a GPS antenna. The submarine grabs a precise satellite fix, hands it to the SINS computer, and the computer uses the new known position to reset all of its accumulated drift to 0. The clock starts over. The accumulated uncertainty disappears. This is why you sometimes hear that submarines do use GPS. They do. But only when they choose to. And only for a moment. Which brings us to the part that almost nobody talks about. The reason this whole architecture is actually superior to GPS-based navigation, not inferior to it. GPS has weaknesses. The signals are weak by the time they reach the ground, around minus 160 decibel watts. They can be jammed by a transmitter the size of a coffee cup. They can be spoofed, where a fake signal tricks the receiver into reporting a wrong position. In a serious conflict, the assumption is that GPS will be denied. Either the satellites will be damaged, or the signals will be drowned in noise, or adversaries will deliberately broadcast false data. Inertial navigation is immune to all of this. There is no signal to jam. There is no transmission to intercept. There is no antenna to spoof. The system runs entirely on the laws of physics, sealed inside a metal tube, untouchable from outside. A submarine running on SINS doesn't care if every GPS satellite in orbit goes dark. It just keeps going. It still knows where it is. It can still launch a missile. It can still navigate home. This isn't a backup plan. It's the actual plan. GPS is the convenience layer on top. The newest generation of submarine navigation is taking this one step further. The United States Navy is rolling out a system called the ANWSN-12. Built by Northrop Grumman, it replaces the ring laser gyroscope with something called a fiber optic gyroscope, or FOG. The principle is the same Sagnac effect, but instead of bouncing laser beams around a glass cavity, the FOG sends them through long coils of optical fiber, often a kilometer or more of fiber wound into a compact spool. The longer the path, the more sensitive the gyroscope. Fiber optic gyros offer even lower drift rates than ring laser gyros, which means submarines can stay submerged for even longer between GPS fixes without losing positional accuracy. They have no laser cavity to deteriorate, no special glass to manufacture, no mirrors to maintain. They're more reliable, more accurate, and last longer. In a few years, the WSN-12 will be the primary navigation system on every American surface combatant and submarine. Russia, China, France, the United Kingdom, and India are all developing similar systems. The race for the most accurate inertial navigation has become one of the quiet arms races of the 21st century. Step back from the engineering for a moment and notice what's actually happening here. A nuclear submarine, 600 feet under the surface, traveling at 30 miles an hour, with no light, no signal, no view of the outside world, knows exactly where it is. Not because something is telling it, because it's keeping track. It's measuring every twitch of motion, every tilt, every nudge, every change in speed. And it's adding all of those measurements together with mathematics so precise that it can compete with satellites. The most advanced navigation system on Earth isn't the one connected to 24 satellites in geostationary orbit. It's the one that doesn't need them. It's the one sitting inside a sealed steel tube running on physics that was discovered in 1913, refined for the first time in 1960, and perfected for stealth warfare in the decades since. There's something almost philosophical about it. The deepest forms of knowing where you are don't depend on permission from anyone else. They depend on paying attention, on measuring carefully, on trusting the math. A submarine has spent the last 60 days underwater. It has not seen the sun, the stars, the satellites, or the shore. And yet, when it finally comes to periscope depth and raises its antenna, the GPS confirms the SINS was right within a fraction of a mile. That's not luck. That's engineering. If you found this interesting, hit subscribe. Thanks for watching. See you in the next one.